Very good morning to one and all. In this video, we are going to learn about maximum power transfer theorem. This is one of the most widely used network theorem in network analysis, and this theorem is used to determine the value of load for that source will transfer the maximum power. In this theorem, we actually use to find out the value of load for which source will transfer the maximum power to the load. What we are going to do, first of all, we apply Thevenin's theorem. Before going into the details of maximum power transfer theorem application, beforehand we apply Thevenin's theorem. That means what? That means that implies all the necessary conditions that were taught under Thevenin's theorem is applicable here also. All the conditions which was necessary for Thevenin's theorem will be same applicable for maximum power transfer theorem. Why? Because first of all, what we are doing here, before going into the application of maximum power transfer theorem, we are applying Thevenin's theorem across load terminals before applying maximum power transfer theorem. Okay, so we are having different cases here. I have written here case 1. Case 1 means when the RL load is pure resistive. Since I have connected RL here, this is your pure resistive. This arrow marks is showing that you can change it. It could be a variable. It is a variable. Okay. Now what we are going to do now, when we have considered the case 1. Case 1 means when the load is purely resistive. We have to find load resistance RL. We have to find load resistance RL. We have to find load resistance RL. This RL. So that the maximum power is transferred to it. Okay. So this is your case number 1. But I have told you before going into the details of maximum power transfer theorem, we are applying Thevenin's theorem across the load terminal. This is your load terminal. This is point number A and this is point number B. Okay, so we have applied Thevenin's theorem. Let us assume that we have applied Thevenin's theorem across the load terminals of the previous circuit, whatever it was given to us, and now we have Thevenin voltage. This is Thevenin voltage and this is your Thevenin impedance. Okay, this is your load current. IL is your load current. IL is varying. IL will vary as RL will vary. Can we write load current IL as IL is equal to VTH upon under bracket RTH plus RL plus JXTH. I have kept the real part under one bracket and the imaginary part separated from this real part. That implies the absolute value of IL can be written as VTH upon root under RTH plus RL whole square plus X square TH. Okay. So we also know that power delivered to load RL, what will be the equation, or when we write power delivered to load RL, that will be PL. So PL is actually absolute value of IL, I square into R. This is the formula into RL. Now put this IL, this value, put this IL to here. So what we are going to have? We are going to have PL will be equal to VTH square divided by, when it is whole square, so under root will be nullified. So we'll have under bracket RTH plus RL square plus X square TH into this RL. Okay. Now in calculus, we have studied the concept of maxima and minima. In calculus, we have studied the condition for maxima and minima, which is for maximum power, the condition should be the rate of PL with respect to RL dRL is equal to 0. Now you may ask me one question here, or this is very important, something very important to understand, why this dPL by dRL. Dear students, dear friends, I would like to add one more knowledge to your bank of ideas or bank of knowledge, that we are actually going to maximize power. Okay, we are intending to have maximum power, that is power delivered to the load. So it is PL. Okay. Now what is variable here? The variable is what is going to change here. The change is brought into RL. What kind of change? You can actually vary the value of RL. As the load is varying, IL will be varying. So variable is your RL. Variable is your RL. So there is always written for getting maximum value of anything, that is constant upon variable, that is dPL upon dRL must be equal to 0. This is the condition of your maximum power. Let us go to deal with further. Put the value of PL and differentiate with respect to dRL. That will be VTH square under bracket RTH plus RL whole square plus X square TH. This is under one bracket minus RL into 2 RTH plus RL. RTH plus RL. This is bracket closed. This is RTH plus RL whole square plus X square TH. This is your, and that should be equal to 0. Okay. That implies RTH plus RL whole square plus X square TH is equal to twice RL into RTH plus RL. That implies we can actually cancel out one factor from here. So it is here RL square is equal to RTH square plus XTH square. That implies RL will be equal to under root R square, that is RT square plus XTH square. Which is absolute value of ZTH. Which is absolute value of ZTH. So what we are going to have from this? The condition is the RL must be equal to absolute value of ZTH. It means what? It means that the value of RL for which there is a maximum transfer of power from source to load, it is your this. The load resistance RL should be equal to the magnitude of the internal impedance of circuit. This is the internal impedance of the circuit. So this is the RL. What is the RL for which the power should be transferred maximum? It is your this. This is your internal impedance of the circuit. That is internal impedance of the circuit. This was so interesting. So we have learned that the value of RL for which there is maximum transfer of power from source to load is your ZTH, internal impedance of circuit. The next case is, which is case number 2, when the load is complex. Case number 1 we have seen that when the load was purely resistive, and case number 2 we are going to deal with when the load is complex. And what we are going to calculate? We are going to calculate the value of load for which the power transfer from source to load would be maximum. This is case number 2. Case number 2 when it is complex load. So IL load current is VTH upon RTH plus R. Keep real part with real part and imaginary part with the imaginary part. J XTH plus X. This is your load current. Now the magnitude of load current IL will be equal to VTH upon under root RTH plus R whole square plus XTH plus X whole square. Now load power can be given as load power, that is PL. In this condition PL will be equal to absolute value or the magnitude of IL square into R. So it is VTH square upon root. Root has been vanished because of this square. So we have RTH plus R whole square plus XTH plus X whole square multiplied by R. Okay. Now to get maximum value of PL, to get maximum value of PL, denominator of equation should be small. For that select X is equal to minus XTH. So means what? If we are going to select XL is equal to X is equal to minus X of TH and put here, it will become VTH square into R upon RTH plus R whole square. To get PL maximum, what we are going to do? We are actually denominator must be small as possible. To make this denominator as small as possible, what we have selected? We have selected the value of X is equal to minus of XTH. I will conclude later on why we have chosen this. So after this X is equal to minus XTH, the PL will be equal to PL. PL will be equal to VTH square upon RTH plus R whole square and into R. Now To set the value of R, that is load resistance, to receive the maximum power, we apply condition for maxima or minima. Actually minima. What is the condition? dPL upon dR is equal to 0. Okay. So put the value of PL here, put the value of PL here, differentiate with respect to dr and do the necessary simplification. Will get the value of R is equal to RTH. That implies Z is equal to R plus J of X is equal to RTH minus JX TH. We have chosen this X is equal to minus XTH just to maximize the PL. Okay, and the value of R we just have received is RTH. See this. It means what? Z is coming RTH minus JXTH. It means this is your Z asterisk TH, that is Z asterisk TH or Z star TH, which is complex conjugate of internal impedance of circuit, which is this is your complex conjugate of internal impedance of the circuit. This is the condition, the result condition of case number 2. This should be kept in mind. This is very important. Actually, this is widely used, widely asked in your examination and interview sessions. So let us go towards case number 3. Case number 3 is that is load impedance with variable load impedance with variable resistance and fixed reactance. Also, the fixed part of load Jx fixed part of load Jx is transferred to the internal circuit, and added with ZTH. This is your diagram. This is VTH. This is internal impedance value, that is ZTH is equal to RTH plus JXTH. This is your R, this is your JX, and this is varying. This is point B, terminal B, and also impedance internal is equal to RTH plus J internal terminal A. This is terminal B. This is of course VTH. Okay, and this is the load connected like this. This is your R, and Xn is equal to XTH plus X. Okay, so this is the whole situation, this is the whole case falling under the last case of this maximum power transfer theorem, where the load impedance with variable resistance and fixed reactance you have. Now what we are going to do, we will actually try to find the value of that internal impedance, which is actually load value, which is actually enable the source to transfer maximum power. Okay, in this case the value of R is actually Z internal to receive the maximum power. It means what? In this case, which is actually similar to case 1, case number 3 is partly similar to case number 1, where the value of R should be equal to the magnitude of internal impedance to receive the maximum power. That's why R should be equal to Z internal. That is R equal to Z internal, which is equal to ZTH plus JXN, which is equal to RTH plus J of XTH plus X, which is equal to, so the value of R is equal to root under RTH square plus under bracket XTH plus X whole square. Now, this was actually the third case, and we have successfully determined the value of load resistance for which the power transfer from source to load will be maximum. This was the case for AC circuit. Now, what will happen if the circuit is DC? For the DC circuit, the maximum power transfer in case of DC network, we are going to study the next topic. See this. That is the maximum power transfer in case of DC network. Let me draw the diagram, the circuit. That is your VTH this is terminals, name it A and B, and this is load connected across the terminal A and B. Let us say it is load RL, and this is your Thevenin resistance. We have initially and previously discussed that before applying the maximum power transfer theorem, whether it is for AC circuit or DC circuit, we have to apply Thevenin's theorem across the load terminal. It means what? It means what? I am repeating it once again for you all, that whatever conditions and situations were studied under Thevenin's theorem, that is active, linear, bilaterals, all those things will be equally valid and applicable for this maximum power transfer theorem, and also irrespective of AC or DC. Okay, this is the load current flowing IL. IL is flowing across this closed path containing VTH, RTH, terminals A, B connected with RL. Now, IL is given as IL, load current IL is given as, for the circuit, is VTH upon RTH plus RL. Now, let us write power delivered to load, that is PL is equal to I square L into R load, which is equal to VTH square upon RTH plus RL square into RL. This is a PL is equal to VTH square upon under bracket RTH plus RL whole square into RL. Now, we know the condition for maxima. Condition for maxima is dPL by dRL must be equal to 0. This is the condition from the calculus. Now, put the value of PL, put the value of PL here, differentiate, and you will get the value RL equal to RTH. So the load resistance should be equal to the internal resistance of the circuit. Load resistance should be equal to the internal resistance of circuit for receiving the maximum power. Therefore, the maximum power from equation that is the maximum power from the circuit is given by, when we put the value of this RL, that is P max will be equal to VTH square upon RL plus RL. We put this value RT is equal to RL whole square into RL, which is coming VTH square upon 4 RL square into RL. So P max is now VT square upon 4 into RL. 1 RL gets cancelled out, this 4 RL, and this can also be written as P max is equal to VT square upon 4 RTH. Why? Because of this RL is equal to RTH. So we have converted this whole P max equation into Thevenin terms, containing all Thevenin terms, Thevenin voltage or Thevenin resistance. Now see this, maximum power transfer theorem is useful in communication engineering, communication system or communications network. In communication network, where the demand of maximum power is important rather than the efficiency. Okay, when there is efficiency and P max for electronic circuit, in communication network or various electronic circuits, P max is valued. Okay, so instead of going for this efficiency, in those systems we are preferring P maximum, and it is achieved by maximum power transfer theorem. The overall efficiency of a network supplying maximum power to any branch is only 50%. Just keep in mind, that is, the overall efficiency is only 50%. For a network supplying maximum power to any branch is only 50%. So use of maximum power transfer theorem is actually very much limited. The use is limited use. Kindly note this. The use of maximum power transfer theorem is actually very much limited in electrical and distribution networks. We have got very much limited use in power system. Okay, where the aim is to get highest efficiency, not the maximum power. Okay, let me tell you once, it is so much important. There is one efficiency and there is another called Pmax. For Pmax, we are having electronics circuit, communication channels, communications network, etc. We value there for this system. For this system, we go for P maximum. So we apply maximum power transfer theorem. But for power system where distribution and transmission is concerned, efficiency plays vital role. Efficiency plays vital role, and we are not applying maximum power transfer theorem there. It is limited there. Okay. So this was all about the maximum power transfer theorem. We have studied all the cases along with the fourth one, the DC network, the DC one. See this? Okay. We are going for next topic, that is on numerical on maximum power transfer theorem. The numerical on maximum power transfer theorem will be based on Thevenin actually. While calculating, while having derivation, we have seen that the maximum power transfer theorem is actually very much dependent on Thevenin's theorem. I have told you while studying Thevenin theorem that Thevenin's theorem is much widely used theorems in network analysis at your basic or intermediate level. Let us have questions. That is, this is a circuit. This is plus minus. This is 50 angle 30 degree volt. This is J4 ohm. This is 5 ohm. This is capacitor of value minus J3 ohm, and this is your terminals through which load resistor is connected. Load resistor is connected and the value is RL. Let us say this is A and this is B. This resistor is 3 ohm. Now, this is question based on maximum power transfer theorem. Now we have to find out the value of RL. RL should be what? The value of RL. What should be the value of RL so that the maximum power can be transferred to load RL from the source? We have to find out the value of RL for maximum power transfer from source to load. So let us start. Before applying this maximum power transfer theorem, I am repeating it once again. You have to keep in mind that before going into maximum power transfer theorem, you have to just calculate RL for Pmax. Let us start with from Thevenin's theorem. That is, let us find ZTH. for ZTH across terminal A and B. What we are going to do, the voltage sources will be short circuited and whatever current sources will be there will be open circuited. Now this will be the circuit. This is 3 ohm, this is J4, 50 angle 30 degree volt will be shorted out, short circuited. This is 5 ohm, this is 3 ohm, this is J4, this is short circuited here, we have short circuited here, this is 5 ohm resistor, this is minus J3 ohm, and this is your terminal of load resistor through which we are calculating ZTH. This is A and this is B. This is, now see this 3 ohm resistor, J4 resistor and 5 ohm resistor all are in parallel. So let us just add in parallel first of all 3 ohm resistor and 5 ohm resistor, and then after this real and real resistors has been added, we'll add real with the imaginary resistor, this J4. The circuit will be now 5 parallel 3, which is 1.87 ohm. This is J4 ohm, and this is minus J3 ohm, terminal A and terminal B, terminal A and terminal B, and through this we are watching to calculate ZTH. Now this is in parallel, so we are going to add in parallel. J4 is in parallel with 1.875. This is 1.875. So it is J4 into 1.875 upon J4. This is J4 plus 1.875, which is coming 7.5 angle 90 degree from this J, and 4.4176 into, sorry, angle 64.88 degree. So now that is equal to 1.6977 angle 25.12 degree. This is in polar form. Let us convert into Cartesian form or the rectangular form. 1.537, that is complex form. 1.371 plus J 0.72 ohm. Therefore ZTH will be equal to minus J3 plus 1.5311 plus J 0.72, which is equal to 1.5371 minus J 2.28 ohm. This is your value of ZTH. Now, as the load is purely resistive, so from maximum power transfer theorem, RL is equal to ZTH, that is equal to root under 1.5371 whole square plus 2.28 whole square, which is equal to 2.7497 ohm. So precisely it can be written as the value of RL is equal to 2.75 ohm. For this value of RL, the maximum power is transferring from source to load. This is your answer.